Alright, so today we're going to be going over Lab 6. So the analysis of water flowing through streams is very important in terms of geography, because the water, how fast it's going, the width and depth of the channels all affect how sedimentation and deposition happen, how different types of channels form. Like, for example, the alternating ridges and valleys found in the Appalachians, including Choccolocco Mountain, which is directly east of our campus. And the valley where JSU is located was produced by water-power differential erosion of folded and faulted rocks. The resulting sediments are then carried away in different streams, creeks, rivers, and so on to be deposited and possibly turned into sedimentary rocks. So, what does all this mean? So, we're going to get into that. So, stream discharge and stream geometry. So, in order to talk about this, we need to know what a stream is. A stream can be generally defined as a long and narrow flowing body of water in a channel. So streams can be a variety of things. Most of the time people think of streams as these tiny little creeks, which are technically right, but streams can also be large rivers like the Coosa, to small streams such as the gutters in your house. So, and a very important variable of streams is their discharge. The discharge is a volume of water flowing by a point over a given period of time. So, for example, imagine you are standing by a stream and you watch the water go by. So, if the stream has a discharge of, let's say, 1 cubic meter per second, that means that you're standing by the stream and 1 cubic meter of water is flowing by you every second. We're going to be learning how to calculate this discharge. So, discharge can be calculated using the continuity equation. So, the continuity equation is Q equals W times D times V. So, that essentially means Q, the discharge, is equals the width of the channel times the depth of the channel times the velocity of the channel. These can be measured in any units as long as the units match up, but it's most commonly measured in cubic meters or meters. So it can be measured in feet, inches, anything really, as long as the units match up in the equation. I'll go over the first two exercises with you. The first exercise says, what is the discharge of a stream that has a velocity of 4 meters per second with a width of 5 meters per second, or 5 meters, and a depth of 2 meters. So, it's a simple equation. We just multiply these two. That would be 10. And then 10 times 4 is 40. So, we would know that a stream that has all of these variables would have a discharge of 40 cubic meters per second. And it is very important to label your units, so do not forget that. In the second exercise, we're switching over to feet. So, if the stream has a velocity of 3 feet per second and a width of 20 feet, and then a depth of 5 feet, so 20 times 5 is 100 times 3 is 300. So this stream would have a discharge of 300 cubic feet per second. Alright, so next we're going to be talking about channel geometry, which are the variables that we just talked about. The velocity, width, and depth, and even the discharge are the geometry of the stream. And these things can and will change. Streams are not a very steady thing. Their discharge, their widths, their depths, their velocities change all the time. Let's say we assume for the last question we did that the discharge remains constant while the other variables are changing. We can rearrange this equation to solve for the new velocity, width, or depth. So it's kind of like an algebra problem where you can swap around some things, and instead of multiplying, since you're bringing something around to the other side, you're dividing. Think of it like that. So it talks about how you would do that, and so essentially we got 300, then we divide that by a width of 10 feet times a depth of 6 feet. Alright, so we know that 10 times 6 is 60, and 60 divided by 300 is equal to 5. So that means the new velocity of this stream is 5 feet per second. Alright, so I'm going to go over a couple of these exercises with you to make sure that the foundations of this are cemented. So for the next exercise, it says that the stream has a discharge of 48 cubic meters per second. And so it has a velocity of 4 meters per second, and then a depth of 2 meters. What is the width? So we multiply that, we get an 8, and then we divide that, and we get a 6. So the width would be 6 meters. Next, we have if the stream above slows down to 2 meters per second, and then the depth drops to 1 meter. What changed? So, 1 times 2 is 2, divided by 48, that is 24. The new width of the river would be 24 meters. So next we're going to be talking, or the question has more of a geometry thing to it. So, if the stream has a discharge of 200 cubic feet per second, and then its width is 20 feet, and its velocity is 2 feet. And then a half a mile downstream, its discharge is increased to 300 cubic feet per second. And then its width has actually decreased to 15 meters, or 15 feet, while the velocity stays the same. So first, let's solve these. So 20 times 2 is 40, and 40 divided by 200 is 5, So we know that this has a depth of 5 meters. And on this one, we can have 30, and 300 divided by 30 is 10. And so we have a depth of 10 meters on the second one. So, it asks, how else must the geometry change to accommodate these downstream modifications? So essentially, what that means is if one thing changes down the stream, other things have to change as well in order to make up for the numbers. So you see right here, the discharge is 200 feet per second, while downstream is 300 feet per second. In order to accommodate that change, the velocity did not change. So that means something else had to change. If the water is not passing by faster, the width has to get smaller and the depth has to get deeper in order to shove more water through. Or inversely, the width could just get wider while the depth stays the same. Alright, I will leave the rest of the exercises up to you, but next we're going to be going over storm hydrographs. So, as we know, the discharge of a stream can vary greatly, and that is also dependent on the weather the stream is experiencing. So if it is raining, it gets water from the watershed and the discharge increases. Inversely, when it's kind of dry and there's no rain, the stream is not getting as much water as normal, and so the discharge decreases. So, when a rainstorm begins, the discharge of the river will not instantly increase, however, so it takes a little bit of time for the rain to reach the river. So, in the lab manual, it talks about envisioning a rural scene with rain falling into the woods. Much of this water will infiltrate directly into the soil, and it will never reach the stream. And any water that does accumulate on the surface will flow slowly downhill to a stream. So, on its journey through the woods, it has to navigate through difficult paths such as rocks, leaves, grass, plants, and other obstacles. Finally, the runoff will pour into a small rill, which will then flow into a gully, which will flow into a creek, and then finally it will flow into a river. So in this rural area, it may take hours to days for the rainfall to actually reach the river and produce an increase in the discharge. So the delay between the rainfall and when the discharge increase actually occurs is called lag time. Lag time is measured as the time between the middle of the rainstorm and the time of when the discharge reaches its peak. Lag time will also vary depending on the characteristics of the watershed. So as we talked about, a rural area, it takes a little bit of time for the runoff to reach the river. But if it's in an urban area, there's not as many obstacles for the rain to get to a stream or a place to sit. So, as you know, in urban areas, it's mostly concrete. The roofs of buildings, the ground, they don't normally absorb water. So more water is able to flow, which means it's able to pick up in velocity, which also means that it is able to get to its destination faster. So Streams with short lag time tend to be called flashy, which is where the term flash flood comes from. And that is where such high discharges of the flashy streams produce the flash floods. So that is why urban areas are more prone to flooding than rural areas. So, as you know, even though urban areas tend to flood more often because of the runoff through the area all at once, these impermeable surfaces also mean that the water will subside faster. So the water gets there really fast, but it also leaves really fast. This is called a rapid return to base level. Base level is the volume of discharge that was in the stream before the storm occurred. So, and it returns to that, and the storm flow has moved through. In urban areas, floodwaters rise quickly to flood peaks, and then they rapidly subside. So if you live in an urban area, you'd often notice that when it rains, it sometimes puddles up and stays there, but it often just goes away after a little bit as well, unlike rural areas where the water is slow and it absorbs into the ground and such and so on. Also, rural and urban areas also have different base levels. Since rural areas slowly release waters into streams, base levels tend to be relatively high. The impermeable surfaces of urban areas, however, release all their water all at once. So in between rainstorms, the base levels are relatively low or often zero. Alright, so next we're going to be creating and using a storm hydrograph. So, some rainstorms fall into two watersheds, one urban and one rural. Each is drained by a separate stream. Geographers measure the change in the discharge over time for both streams. This data is contained in the attached figure. So in your book you'll have a figure like this, and to simply put, we're going to plot it onto this graph right here. Alright, so first we are going to plot the discharge data on the following data sheet, where the x-axis is equal to time and the y-axis is equal to discharge. You will then have two overlapping graphs. One will contain data for Slapneck Creek and the other will contain data for Possum Creek. After plotting it, we will indicate the time the rainstorm occurred and the time of peak discharge for each creek. Then we will discover what the lag time is for each creek and which stream is flashier. Finally, we will talk about which is the rural stream and which is the urban stream by only looking at its data. So I will show you how to plot a few of these. It's relatively simple, and you will go ahead and finish that on your own. Alright, so we're going to be plotting the discharge of Slapneck Creek and Possum Trot Creek. So, on day 1 at midnight at Slapneck Creek, it had a discharge of 11, so we're going to put a dot right there. And at Possum Trot Creek, it had a discharge of 5, so we're going to put a dot right there. So, day 1, 6 a.m. Slapneck had a discharge of 15, so we're going to put a dot right here. And then Possum had a discharge of 4, so we're going to put a dot right here. Alright, then day 1 at noon, which is when the rainstorm first started, we get a slight increase in discharge at 16 for Slapneck, and then we get a compared to, let's see, yes, a slight increase as well for possum trot, which is back at 5. Then at midnight we get, or 6 p.m. we get 15 again, and then 9 for possum trot. Then at midnight it increases to 17. Sorry, back in here. And then possum trot almost doubles. So, or it does double. Yeah. So, as you can see, you just fill out the graph like so, and you will be able to answer those questions as well as do the hand-in assignment.